Hello, good evening, good day, or good morning, depending on where you are. And welcome to the annual evening seminar organized jointly by the FACS, Formal Aspects of Computing group of the British Computer Society, jointly with the Computer Science Committee of the London Mathematical Society. My name is Andrei Popescu, and I am the liaison between these groups. In the list of panelists, I'm also joined by Professor Jonathan Bowen, chair of the FACS, and Mr. Kieran O'Connor, event organizer for the London Mathematical Society, going to help us if we get in any technical trouble today. Today, I have the great privilege of introducing our distinguished speaker, Professor Annabelle McIver, who is joining us from within her 6 a.m. in Sydney, where I believe there are already 22 degrees outside. Annabelle is a professor of computer science at the McIver University and co-director of the Future Communications Research Center. She studied mathematics at the University of Cambridge, and she has a doctorate in mathematics from the University of Oxford. And she's a world-leading expert in quantitative formal methods, which include the formal verification of quantitative probabilistic properties of programs, and also the foundations for quantitative information flow and for analyzing security properties. Probabilistic behavior of computing systems, which is Annabelle's research area, is both beautiful and technically very demanding. So we are in a sweet spot here. On the one hand, many of us have the ability to enjoy the end results, such as those produced by Annabelle, but on the other hand, very few of us can actually produce interesting results in the area. Much of Annabelle's work is published in major top-tier conferences, including LIX, CCS, POPL, CONCAR, and TACAS. She was an invited speaker at CONCAR 2020 and actually a plenary speaker at the ConFest conglomerate of conferences, and also an invited speaker at CSL 2022. She has co-authored 2 important books in formal methods, which have become standard references in the area. And these are Abstraction, Refinement, and Proof for Probabilistic Systems in 2005, and The Science of Quantitative Information Flow, more recently in 2020. So we're all going to enjoy Annabelle as a speaker today, but I should add that I and many others have also very much enjoyed reading her papers over the years. Speaking for myself, whenever I want some clarity and when, so to speak, I crave for some elegance, about various subtopics of quantitative information flow, security, I look to see what Annabelle and her collaborators had to say about that. In other words, I take a cure of some of her work. She, as well as her collaborators, including, of course, Carol Morgan, develop concepts from first principles, often via successive proposals, which they themselves challenge and refine incrementally. So after such merciless self-scrutiny, the concepts stand strong. And the concepts are convincing not only thanks to their impeccable mathematics, but equally importantly, I would say, or perhaps even more importantly, thanks to thoroughly motivated definitions grown organically from the motivating examples. There is no arbitrary choice in Annabelle's introduced concepts. So while she is, as far as I can tell, a classical logic mathematician, there is no axiom of choice in her conceptual development. Though admittedly, there's plenty of probabilistic choice. Now, without wanting to take too much time before I hand over to Annabelle, I cannot refrain from giving a personal example of the wonderful unifying clarity spread by Annabelle's and her collaborators' work. And this is just one of the many examples. A great deal of papers in quantitative information flow security take for granting the necessity to employ the good old standard notion of entropy for measuring the amount of leakage of information, and therefore to assess the information flow security of a system. And as a young postdoc working on a security project, I have often wondered why this choice goes unquestioned. But it didn't actually go unquestioned. In the paper Axioms for Information Leakage by Annabelle and collaborators in 2016, I found a crystal clear exposition of when one should use standard entropy, and importantly, when and why some different measures are more appropriate, all sharing certain entropy-like properties that qualify them as measures of leakage. So just to summarize, I love Annabelle's papers because while the mathematics of the what stands by itself, the why aspect is also abundant. Okay, The titles of today's talk by Annabelle is Probabilistic Datatypes, Automating Verification for Abstract Probabilistic Reasoning, where she will walk us through the challenges of keeping separate the verification of the data types themselves and keeping separate the verification of the data types from that of the programs manipulating the data types in the presence of probabilistic behavior. And I challenge you, the audience, to find anything arbitrary in the design decisions behind her solutions. Now, as a matter of logistics, her talk will last for about 1 hour, and she will take questions at the end. For questions, you can use the Q&A window, or you can raise your hand, and we will unmute you. So, Annabelle, please.
Well, thank you very much, Andre. But, you know, challenges are really excellent because that's what gets you to the right, you know, being able to get good definitions for things. Okay, so thank you, everybody, for coming today and for inviting me to speak at this evening seminar. And the sun is just coming up here in Sydney. And yes, it is a little bit hot, but we did have a good thunderstorm last night. So most of today's talk will be about how to reason efficiently about programs that have probability. And we want the proofs to be efficient enough so that they are going to be amenable for automated checking with sort of modern mechanized proof systems. So, what that usually happens for probability, probability is a very challenging thing for automated reasoners to deal with. And so what we normally do is start with sort of principles and techniques that work well without probability, and we adapt them so that we can actually insert quantitative information in there, so we can start talking about probabilistic properties. We can actually describe some probabilistic properties that we're interested in, and then come up with sort of reasoning techniques to be able to prove average properties and that kind of thing. So I thought, before moving on to the challenge thing of probabilistic data types and why we're actually interested in them, I thought I'd give a very, very brief history of probabilistic programs and verification for programs. And here it is basically on one slide. You should take that. So reasoning in probabilistic systems is an absolutely massive a topic. And so the highlights that I've put here, you should really think of them as the highlights that have really informed my thinking sort of on this particular topic of reasoning about sequential probabilistic programs. So before the 1980s, there were a lot of really wonderful randomized algorithms that were proposed. And a lot of these were proposed in order to get around known resource and performance limitations on problems where you tried to come up with an algorithm which didn't have probability in it. And of course, obviously, for security, it's really important to have probability for implementations. So after around about the during the 1980s, there were 3 fantastic and wonderful ideas that came out. And they are very relevant. You need to put them all together in order to get what we have at the bottom around about the 1990s, which is the source level reasoning for probabilistic programs. So what were those ideas? What were those 3 things? Well, the first thing that you actually need to have efficient reasoning is to be able to reason at various levels of abstraction. Obviously, you know, we know that in maths, but for automated reasoning, it's actually absolutely crucial. So this was given to us with probabilistic power domains, and one of the most important things that came from there was actually how to compare different descriptions of probabilistic programs. The next thing that you need for source level reasoning is, if you have a program sitting in front of you, you have to be able to interpret what that actually means in terms of some kind of transition system, which is how we imagine that when programs execute, that they execute a transition system essentially. And so this was given to us by the probabilistic monad of Giry. And then once you've got those two things, what you really need to be able to do is to describe some quantitative problems that you want programs to have. And if you have this program text sitting in front of you, you have to be able to lift off the mathematics and connect it to the lift off the mathematical properties, sorry, from the actual program text, and turn it into something which can then be interpreted over these very mathematical transition systemy kinds of ways, so that we can reason at different levels of abstraction. And once we have those three things, I, with my collaborators, came up with this probabilistic guarded command language. So just for people who don't know what that is, the guarded command language was proposed, I think, invented by Dijkstra around about the 1970s or something. Gives us a very simple program to describe complex algorithms and reasoning for that. So we added the P to that, which is the probabilistic, gives us probabilistic guarded command language. And here again on one slide, I will fill this out later with examples as we go through. But what we have is for PGCL, we have non-determinism, which is a bit different from probabilistic choice. Non-determinism is absolutely crucial to be able to summarize complex behaviors using it basically gives us a sort of a way to abstract complex behaviors into simpler behaviors, but which are enough for us to be able to reason about complex problems in a simple way. So what this most important is that we have this refinement relation. So if you imagine that P and Q are different descriptions of an algorithm, essentially the same thing. If P is described in a much simpler way, a much more compact way, we can do reasoning over P, and this refinement relation, which comes from the understanding from power domains, we're able to export those properties to something much more complicated, which is Q. We need to have more complicated things whenever we sort of build a large system. So the second thing that PGCL has is source level reasoning. So source level reasoning is a good thing because you write a program and you want the proof to stick to the program. You don't want it to stick to some abstract thing with no connection between them. So we have this source level reasoning, so P is the description of the program, like in a programming language, and we can write properties. We can put them at, we have a precondition and a postcondition, and that allows us to specify what we want the program to do. And it also comes with a reasoning system, a logic as well, which allows us to prove properties so that we can prove that the program actually does what we want it to do. So in the PGCL version, the phi and psi are actually real valued functions. They're interpreted as real valued functions, the real values we need to be able to specify probabilistic and average properties. And then, of course, the logic has to be able to deal with that. So the challenge here is really at the bottom. So in theory, we can do reasoning on the source level for complex probabilistic programs. But the reality is that we need to be able to have automated checking, because a lot of these proofs are they're very detailed, and you can make a lot of mistakes. You can make a lot of mistakes if you just do it on pen and paper without probability. And with probability, it's exponentially worse. Right, so this is the challenge at the bottom. We want to be able to automate all of these things, but I thought I'd begin with a specific challenge program, because as you build these, as you build sort of theoretical frameworks and logics and that kind of thing for this area, what you really want to be able to do to make sure that you're sort of capturing the right things, making your logic do the right things, is that you come up with these really tough nut problems and see whether what you've proposed is actually going to work well. So this, although it's a very few lines of code, turns out to be really, really tricky for probabilistic verification. So what does it do? Well, so I've given you a hint at the bottom here in blue. It is a probabilistic guarded, it's written as a PGCL program, probabilistic guarded command. We've seen some of the things that I've mentioned already. So we have a post condition and we have a precondition. You can see that the precondition has a 1 over n. So n is some constant value, some just constant value for the particular problem at hand. So what this is doing is we want to set some variable c, which we have here, uniformly between n things, 0 and n minus 1. So the post condition for this program, I'll talk a little bit about this in a little while. The post condition says we're interested in having c. So how do we formalize this idea? Set c uniformly between 0 and n minus 1. So we say, well, when this thing terminates, we're interested in looking at what value c has. So c can take a value I, and here we have I lies between 0 and n. And the precondition tells us something about some more information about c ending up in a particular value I. The precondition normally says, if you begin with this precondition, you definitely have to end up with the postcondition. But for probabilistic PGCL, we can say the precondition, you don't have to end up with c equals I definitely, but you do have to end up in that postcondition with probability 1 over n. So this is where the precondition and the postcondition is now able to give us some what we want, what we want the program to set C uniformly, and the precondition and postcondition just summarizes that formally. And the reason that we have to do it formally like this is because we need to do some reasoning to prove that. Because this doesn't set C uniformly, in a straightforward way. It has a while loop, so it goes into a loop. So it's got this variable v, which we compare to n, and c also, which we can compare to n. And then v and c are set during the loop operation, provided that the guard for whichever command is true. So if v is less than or equal to n, v is doubled, and c is set either with probability 1/2. So we have that in our language now, 1/2 with we either double it or we double it plus 1. Anyway, around and around we go. And eventually this is set uniformly between 0 and n. And at the moment, there are only informal proofs that this is the case. Now, mathematically, you can if you think about it for a while, you can convince yourself that this is right. But we want to do a formal mechanized proof for why it's correct. So this does seem to be a challenge. The reason that it's a challenge for formal proof is because of the need to find an invariant. So again, it's standard for doing proofs like this is if you have a while loop, in order to prove it, you need to find some invariant property which summarizes what's happening around here and which then simplifies at the end and at the beginning to give us the property that we want. Now, invariants are often quite tricky to find. There are some tools which can help finding invariants, and then the mechanization can actually check that they really are invariants. But when you add probability, you need to put in not only invariant information about the state, what properties are being maintained as we go around the loop. We also have to put in probabilistic properties as we go around the loop. And the problem for verification is that for this particular problem, it does not seem at all easy to be able to write a compact invariant which works for all of n. If you fix n to a particular value, you can break your head trying to actually find out what the invariant would be for n equals 5, let's say. But to find a compact invariant which works for everything is doesn't seem at all easy, either for humans or for proof at the moment. So that means that's why this is a challenge problem. So just to give you a little flavor, again, for this challenge problem, I thought I'd just iterate around, and what we'll see is we'll actually start seeing some invariant properties, so that we know that there are some invariant properties there, but it's actually trying to describe it in this sort of this way of writing a real valued function, which is maintained as we execute this sort of transition, thinking of it as a transition system. So I've actually color-coded the program so we can see what happens. I'll iterate through in a moment. So green is for the initialization, yellow is for states produced with this command, and blue with this command, and red is a color states red if we've terminated, because the guard says this no longer holds, and the guard says we can't go around the loop anymore. Okay, so we start with C and V to be 0 and 1. And we execute the yellow guard, so we get C is set to 0 or 1. So we get the split here. So this is probabilistic choice. I haven't written the probabilities in, but every time you see this sort of binary split from a state, it's because we've executed that probabilistic choice. So we'd say that happens with probability half, or that happens with probability half. So after one iteration, this is where we get. After two iterations, we have 4 things. After 3, so I've set, sorry, I should have said at the beginning, n is 5 and I is 3, I think. So after 3 iterations, I think we now have all of these red states. Now, I should have said at the beginning that to set a variable uniformly between 0 and a power of 2 is very easy and quick. Basically, you would just keep iterating the yellow until V got large enough. But the reason that this is a trickier program is because we're considering n's not powers of 2. So we have n equals 5 here. So what we have, the good thing though, is that we've got these 5 terminated states. So we've terminated there, and you can see that there are only 5 different things. And if you actually trace down and work out the probabilities for each outcome, you'll see that the probabilities are all exactly the same for those red states. But we do have these yellow ones here that have not terminated. And so we have to keep going, and we keep going by executing the blue, which shifts everything a bit if you sort of have time to read this. But then we have to keep going and going. Now, if we wrote an invariant which included the probabilistic information, so all of these sort of branching and the way that they sort of, all the probabilities accrue for those kinds of things, it would have to be included for all of these states. And this is only n equals 5. Okay, so we need to have an invariant for, you know, n is anything in order to get this program proved. Just one quick word, the reason it's done like this, that there are much easier programs for generating uniform distributions, but they're not very efficient. So this is an efficient one, largely because it doesn't waste randomization that's already occurred in these kinds of things. Anyway, you just need to think about it, and I'm happy to answer more questions about that at the end. So the main point here, though, is that the invariant for capturing all of this behavior, even for very small values of n, is very complicated, and it doesn't seem easy to be able to generate a general one. All right, so what exactly should we do to do this? Because we're determined to get this this simple program, seemingly simple program, done in a way that we can actually automate it. So what we do is we actually go back in time, even before 1980 to 1974, and look at a time where people were dealing with not probability, but they were dealing with this problem of having too much information and somehow needing to reduce the complexity of that, so that big complicated systems could be developed in a way with some kinds of assurance that it was actually doing the right thing. And so the idea of Barbara Liskov and Stephen Zillers has been extremely influential in programming. And it was this idea of abstract data types. You can see that it's influential because it appears in sort of modern programming languages as interfaces, which provide an interface between someone who wants to use a library, which gives access to some encapsulated data, and it gives ways to access the data in a simple way, described in a very simple way, so that you can actually just think at that level of abstraction. So again, I talked about different levels of abstraction. So you want to be able to, when you build a system, you want to think at an appropriate level of abstraction, but at some point you need to get into the details and do all of the hairy stuff in order to get the whole thing working. So Barbara Liskov and Stephen Zillers pointed out that there was this difficulty in developing large systems, in that programmers that actually wanted to develop a sort of develop a program that worked in a particular domain, they ought to be able to think about the concepts of that domain, right? Rather than actually thinking about data types, rather than actually thinking about sort of data structures and, you know, complex data storage and that kind of thing. But that still has to be done, and these things have to be connected together. So that's very much what's happening in our challenge problem. We want to be able to think of simple uniform distributions or something, but we're confronted with all of this information which sort of pushes us away, and it's sort of overwhelming, and we can't actually see the uniform distributions inside of what's happening. So a very quick, so a lot of the talk now is going to be about how to connect sort of simple descriptions of things with more complicated descriptions of things. And I'm going to do it through this idea of data types applied to probability. So just before we get started on that, I just want to show you a very quick example of essentially a very simple description of something which has a much more complicated implementation. I'll show you first of all without probability, and then we'll add some probability. So suppose I wanted to write a program which was an educational program, and it was to do with sets. Well, when you were developing the program, you'd only want to think about sets. So you would say, well, I want to, formalizing this a little bit in a programming language, I would say, well, I want to have a set, and these are for school children. So these sets are really very simple. They're just finite. I just give it some value n, and I just want to be able to talk about sets of size n. So what can we do with sets of size n? Well, we can make it empty. We can add an element to a set, or once we've got a set around, then we can give it an element and say, is that element in the set? So the important thing about here is that we're just talking about sets, right? Now, we do want to develop something which somebody has to choose a way to represent a set. So this is the way that a team of programmers would work on this. So he or she would want to develop a user-based implementation of sets. She would want to declare a set, add some elements to a set, and just ask whether some value is inside of a set. And that's where she wants to think when she's developing this sort of educational system. This guy on the other side, however, he needs to be able to implement it. So he's thinking, oh, do I use a linked list to represent the set, or do I use an array list, or, you know, all of these kinds of things. And then he has to actually make the algorithms to make all of this work. So how do these guys communicate together so that when she's thinking about a set and she calls these functions that he implements, well, they look at the abstract description of what the set should be, and he also goes away and implements these things, and then he produces a proof to show that what he implements is delivering this so that she is happy. So how is this all? So we'll give just a couple of little definitions for this. And then we'll go in and start adding probability. So sort of towards maths, we say definition, an encapsulated data type is a triple which has some programs, which is we have to initialize the data type, and then we have a set of operations. So those were the ways to access the data, which is given by this OP. And then for mathematical purposes, we have to finalize it, but we don't need to worry about that so much today. So that's what an encapsulated data type is. The most important thing here is that so this set data type would be the set of operations would be make it empty, add an element, see whether an element is in the data type. So they would be in the operations OP. Now she would be writing a program, and this is given by this calligraphic P here. So you imagine that you write some program and you only access the data type by calling the named operations. Okay, so that was her program that she was writing on the right. He, however, is going to be implementing these things. So his version of the data type is still going to have the names of the stubs, but his is going to have a whole swathe of complications because he is actually doing the work to represent what she is trying to do. And then the refinement here says, well, if we have a much simpler idea in the domain, right, of relevance of what the program is going to do, and we're happy with that, we need to be able to prove that what he is implementing with all of the complexities that he has to cope with, we have to show that all of the properties that she wants to have are satisfied by what he's writing. And that's what the refinement relation gives us. So we have to be able to link these two things specifically and come up with compact proofs to be able to show that all of this works out. So what's in the rest of today's talk is that, first of all, I'm going to change the data type a little bit. I'm going to add probability. And what happens time and time again is that when you have something working beautifully, so the traditional proof method for doing that refinement that I just showed you is to use simulation. But it turns out that when we add probability so that we can have abstract descriptions of probabilistic properties and relate them to complex descriptions of probabilistic properties, we'll find out, so we've got a spoiler alert, that things start breaking. They don't work anymore. So rather than despairing, we sort of look more deeply at what's going on, try and figure out what's making things not work anymore, figure out what has to be changed in our way of thinking about this. And then we'll get something which actually gives us a better understanding of what's going on with probability, and we'll be able to use a lot of the ideas that give us these compact proofs so that we can link simpler properties, simpler behavior to complex behavior. And then we'll see whether it works for our challenge program. And also in the end, I'll say very briefly about what it's got to do with information leaks in programs. Okay, so what happens when the data type is probabilistic? Well, so here is an abstract specification for a data type, and it's got probability inside of it. So we have our initialization, which, so I said the data type needs three things: an initialization, finalization, and an operation. This only has a single operation. The initialization doesn't really do anything. But what the operation does is that when you call this flip function, an internal coin is flipped either heads or tails with probability 1/2, and then the value that it ends up with is returned through the when it's called. And the finalization, again, we won't really worry about finalizations today. Okay, so now we've given it to our developer, and she's going to write a little probabilistic program. Okay, so she's got this data type. So this is how she thinks about probability at this point in time. She knows that if she just flips a coin, she looks at what this is supposed to do, and it just flips a coin, and she gets the value when it flips. So now she writes this program. Again, she needs to have this initialization and finalization for the formal reasons, but this is really what she writes. She introduces a new variable v, and then she non-deterministically chooses a head or a tail. Now, this non-deterministic choice, I mentioned that this was given to us from being able to write abstractly, to write down behaviors which happen, but gives you a little bit of an abstract handle on them. So she says, well, v is set, and I don't care how it's set. I just want it to be set to a head or a tail, and I don't care. It can be set on the basis of the weather. It can be set on the basis of, you know, I ask someone a question and they give me an answer, and on the basis of that, I choose whether it's head or tail. Anything at all that this non-deterministic choice can be set. But after that's happened, so we know what v is, then she calls flip, okay, and she sets a variable g to the result of flip, and flip is this coin, okay. And now she says, right, so what's the probability that g and v have the same value finally? Okay, that's a probabilistic property. So given that she understands that, so we've got this little class over here who's going to help us with questions like this. So we asked the class of keen students of probabilistic programming, and they say, well, basically the answer is going to be half. Why is it going to be half? Well, because the flip happens after v, and so whatever v is, we know what v is. If you imagine stopping the program here, you can actually see the value of v, and then the coin is going to be flipped, right? And it's just the way it behaves, the way probability behaves. So whatever, if v is a head, then with probability 1/2, the flip is going to set g to a head. If v is tail, then with probability 1/2, it's going to set g to a tail. So it's got to be a half, right? Okay, so what we're going to do is we're going to try to do this a little bit more formally. So we say, well, we'll start with a postcondition and a precondition, and to understand how that's working. So we set the postcondition g equals v, and just like the program I showed, the challenge program I showed you at the beginning, there's some probability p here, which is the prediction of what the value g equals v is going to be. So we think that this ought to be a half. Now, what I haven't shown you, but what I'm going to show you very quickly now, is that once we have probabilistic guarded commands, and we've applied power domains and the Gieri monad and all of that kind of thing to it, what we can basically do is we can work backwards, starting with the postcondition, and we can apply the way that this works operationally to generate preconditions. And this is called WP, so weakest precondition of a program, where the postcondition is g equals v, and we end up with a precondition. We can now have real values. So if the class are correct, and this should be a half, when we apply all of the rules for manipulating this back through the program, which I'll show you very quickly in a moment, we should get a half. Okay, so let's do that. So we start with our postcondition. Well, skip doesn't do anything, so we end at the precondition when we have skip here, and essentially we're referring to the specification over here. When we have a skip, it doesn't change anything, so the precondition and the postcondition are the same. Now we have to, oops, beg your pardon. Now we have to go back through the flip. And what that does is we use the operational knowledge that flip just sets something to 1/2 one way or the other. So we can, there's a very simple syntactic rule which we can apply in order to get this expression here. What this expression here is saying is that if v equals h, then we have 1/, chance of getting g equals v. And if v equals t, then we have a 1/, chance of getting g equals v. Okay, and that, again, is a very mechanical way to do this. There's actually automated tools which will do this for us. On we go. Oops, sorry, I keep pressing the wrong button. On we go. This is a bit more complicated. We go through the non-deterministic choice, and we basically just do a variable update, and then we take the minimum between the expressions that we get, and that simplifies to 1/2. Okay, so great. And then we go through the initialization to get 1/2 at the beginning. So the class were perfectly right. Well done, class. So that's what we're expecting. However, we imagine now that, so we can understand this a little bit differently to show that we get this 1/2. And there's something which is called the copy rule, which is essentially what we were doing. We were referring to the specification as we went backwards through that whole thing. But essentially, we could actually just write down the code from the implementation directly and get a piece of code which is longer, but it's essentially doing exactly the same thing. And that's exactly what we've done here. And so that's called the copy rule. And so the way that you understand how a data type works when you just have the code of the data type and function calls, the way that you can understand that working is simply write in the program, the implementation for those function calls. And that's called the copy rule. And you can there's people usually call it inlining. Okay, so what we're really interested in is refinement, because of course we need a more complicated implementation of this thing for whatever reason. So on the right-hand side, so on the left-hand side, we've got this abstract data type, and that's how she will think about how this will work. On the right-hand side, we have an implementation. So he's gone away and he's come up with this really wacky idea for how to implement this. And it's that what he's going to do, he's going to prepare a flipped bit, but he's not going to tell anyone. So so an implementation of this is that at the initialization, he's going to flip a bit ready, and he's just going to keep that secret. He's not going to say anything. He's just going to save it somewhere that she can't access. Okay. And then when a flip is called, the variable coin, whose value is returned, is first set to that secret pre-flip. And then C is set again for next time. And then, as I said, the coin is returned. And he has this idea that he should do that because it'll be quicker. She'll get her coin done, received more quickly, because this can sort of happen in the background and she doesn't know anything about it. So she can get it quickly. So he reckons that this is a good implementation for her. So this is the abstract. The abstract way of thinking about this is actually using this hidden variable in order to facilitate these coin flips. And he's arguing that shouldn't matter because she doesn't know. She doesn't know until the moment that she actually wants to look at the flip. So now let's see formally whether that all works out, whether we've got the maths right for doing that. So the way that non-deterministic choice works for the mathematical model, which interprets all of these things, it's a bit like a Markov decision process. The non-deterministic choices, the totally random, who knows how they're set choices, must happen before the flips. And we have this semicolon here, which provides the instruction, right, that this happens first. And when this is finished, only when this is finished, can this happen. Okay, so in particular, when there's not been a pre-flip of a local variable, so in particular, when there hasn't been a pre-flip, right, then this G cannot determine what's going on here at runtime. So when nothing is known here about any internal state, this shouldn't be able to be able to access it. So now let's see how they're doing. So these data types, he's reasoning, should be the same because she doesn't know anything about that. And the sequential composition means that we can't insert behaviors, you know, before things. So the sequential composition says this has to happen, then this has to happen, and then this has to happen. And the fact that we've isolated this means that she can't access it. Okay, so what she thinks, the behavior she thinks should happen, should give us the 1/2 probability property that we had before. Oops, beg your pardon. I'm not sure. Oh, sorry. Getting ahead of myself. I'm not sure what I touched. Okay. So let's try doing the inlining trick for his implementation. Okay, so if the inlining, remember, should correspond exactly to how you understand how this executes, but also some of the things ought to be hidden as well. So when we inline the program, so now we have a more complicated initialization. We have I've simplified this a little bit, but essentially coin is set to C, and then C gets set probabilistically between head and tail, and then G is set to coin. And then we just finish off. We're not bothering much about the finalization. So again, remember what we're doing in the original PGCL, we used a Markov decision process interpretation, and we're still using a Markov decision process interpretation, even though we've got we're working with him who says he's done something which shouldn't matter. So the question is, does it matter? Well, unfortunately, for a Markov decision process, it does matter, because when we go back through the WP and calculations that we did before, what happens is that because the eventual value of coin is going to be set, of G is going to be set to coin, which is set to C, and C is set before the non-deterministic choice happens. Okay, so when we inline it and we use a Markov decision process interpretation for this, the Markov decision process doesn't care that she can't see that has been set and that he was relying on, and it says no, the probability that G equals V finally could be as low as 0, right? Because the way the way the semantics works, the interpretation as a Markov decision process, is that this non-deterministic choice essentially has access to all of the state, even when parts of it is supposed to be hidden, which was his sort of like main idea. So we've unfortunately we have things aren't looking so good, but have we actually broken anything? It's only the problem of maybe his implementation is wrong. So let's have another look at refinement of data types. So another way to think about refinement of data types is actually to use something which is called a simulation. So if we have two different data types and we have abstract ones with I, OPs, and F, and concrete ones which are more complicated where they're all primed, we can say that there's actually a simulation between the OPs and the OP primes if we have this representation function, and essentially the representation function will add in contextual state that is needed by this more complicated implementation. And the refinement means exactly what it had before. So all of the properties of the things on the left transfer to properties of things on the right. So basically what it means is that we can understand how this works by adding in contextual information given to us by rep. So are those two if things are working properly, then these two, this abstract and this concrete, should not be working with a rep. But unfortunately, it does work for a rep. I haven't got time to show you today, but if we take this rep program, which puts in a context of setting C uniformly between head and tail, then these functions, this set of relationships works perfectly well with this set of operations. So we saw that there was a problem possibly with his thinking of the inlining and the copy rule, but it seems that he would say it should be fine because we have this representation function, right? And the two things simulate one and the other. So there's something wrong. So unfortunately, this is where I said at the beginning that something is broken by adding probability. So we had better take a much closer look about what on earth is going on. So how should simulation work? Well, simulation is, as I mentioned before, is a way to relate abstract behavior, which perhaps has a different representation, different variables, with concrete behavior, which perhaps has slightly different behavior, but which can be sort of like, but which is consistent, right? Which is how we get that refinement. And once you have a simulation relation, then you can actually prove refinements between these whole contexts, right? So using the inlining, we think that these two things should not work, but we also have a simulation which suggests that maybe they should. So let's just go through how a simulation would work. So let's start with the abstract and the concrete. And what we'll do is we'll run through these programs, and along the top, we'll track the abstract behavior, and along the bottom, we'll track the concrete behavior, and we'll just see how the simulation is supposed to be adding context so that so if it's working properly, it would say, well, although these functions are in simulation relation, it means that the whole program in a larger context can be simulated. Somehow something's not working here. So let's see us happening. So we have the initialization, so we get here, and then we execute this first branch. Okay, so we can add in the information here. And what happens is if I start here and go down here, I end up by adding in the rep information. I get to the same place as if I had started just doing the single abstract, which, remember, set rep did this preflip. So going that way around, I get to the same place going that way around via this rep. So what happens when I go here? Well, I set V to head or tail, set V to head or tail. Okay, so I think I get things like this, and then I do the flips. Okay, so I ought to be able to prove refinement, but when we did the inlining, that didn't work. So simulation only works as a proof method if it is consistent with the inlining, because I can glue these little proofs together, but maybe there's some other stuff going on that I haven't thought about carefully enough. And it's right here. In order to glue those little proofs together in the way that we expect, in order to use the simulation relation between the little parts of the program to show that the whole thing simulates, we have to have some extra properties which just slipped by us. So in the middle of that little proof, if we were to glue it together to build a proof for the whole program, we would be saying that if we started here, I did the non-deterministic choice, and then I did the probabilistic choice, I should get to the same place as if I did the probabilistic choice first, and then did the non-deterministic choice. So that would be that in our rule, we would have to say that probability and non-determinism, right, even when applied to different variables, essentially preserve properties. But hang on, this is not valid using the Markov decision process semantics. And so what we've found is that by adding probability and trying just to go ahead and using the same infrastructure that we had without probability and expecting everything to work, well, sometimes we can be disappointed, and we're disappointed here. So the reason that, so this is good for us because we now know that we need to think a bit more carefully about simulation if we want to use this as a nice proof technique in order to get decent proofs for complicated programs. So simulation doesn't work when we are using our Giry monad approach to give us an interpretation for a Markov decision process. But hang on a minute, you know, he ought to be able to implement his program in that way. And so what we've learned by going through all of this whole thing is that Markov decision processes do not distinguish hidden state. And if that is what we're relying on, if that is what he was relying on for his implementation, then we no longer have, with the Markov decision process interpretation via the Giry monad, a way to support the thing that he ought to be able to do. I will just point out that when I've given this talk before, and people working in concurrency have said to me, well, it's not surprising and so on. But the thing that's unusual about this is that we're not working in concurrency. So more things are a little bit more controlled when we're not working in concurrency. And you'll be glad to know that, in fact, when we use partially observable Markov decision processes, he is allowed to have his implementation, but we now have it once we understand it at the maths in mathematically, we then have to tell him what he has to do in order to be able to build his idea. So we do have to work with partially observable Markov decision processes. Not only do they have non-determinism and probability, but they are able, in the way that they are formed and behave, can distinguish between hidden state and visible state. And they can work with non-determinism, which only can pick its choices on the basis of certain things, certain observed things, and we can say some things are not observable, and the non-determinism cannot therefore react to that. So a Markov decision process interpretation of this program would take some visible state. So everything is visible. So that's why I've got this calligraphic V. And it will give a set of distributions, which is this bold D, over visible states. A partially observable Markov decision process has to distinguish between visible and hidden. And so the hidden states, well, when you think about Markov decision processes, you start being able to infer things about the hidden state. So in the maths, that's described by a distribution over the hidden state. So we have a pair of things that we know exactly what they are, things that we have some view about what they are, but that might change as described by distribution. And the program will transform something like this into a set of distributions, so hyperdistributions, over things of this type, this pair. So when we do that, it turns out that when we interpret everything properly and carefully, on the Markov decision side, when we try to swap these things over, we do not get equality, but on the partially observable Markov decision process side, we do get the equality. So in maths, so he was actually right. If you get the right maths, you can actually do what you want to do in terms of keeping things hidden. So just very quick, I'm not really going to go through this slide, but just to show you how this program works differently. So here we have the non-deterministic choice after the probabilistic choice. When we interpret it as a partially observable Markov decision processes, we have fewer things, because all this non-determinism sort of knows, if you like, is that there's a uniform choice, but he can't split that up. In the Markov decision process version, everything is visible, so this can be split up, and you can get a lot of different behaviors. So each of these lines is a possible behavior of this program. So we have 4 of these different of these things, but we only have 2 over here. So simulation interpreted with partially observable Markov decision processes now work. However, we've sorted this out in the maths, and we've figured out how to understand inlining. But now we have to say, okay, so now we're actually dealing with hidden state. And what he has to do when he is programming is, if he's got hidden state around, which he is relying on, which is important for his ideas, you know, to be able to implement things nicely, but which it's important that she doesn't know about until she needs to, he has to make sure in his programming that no extra information leaks will occur. And that can be a challenge, but it's a challenge worth having if the implementation is something that you really want. So what have we done? Well, what we've managed to do is look at, we started out with a problem where we didn't have efficient reasoning. Things were too complicated. We went and we had a look at an idea from long ago, which is this abstract data types, where it did talk about things being, where it did talk about how to sort of get some control about this complexity, where on the one hand you needed the complexity in order to get things working, but you don't need to have the complexity when you're actually trying to prove things. We found out that there was a problem with understanding how data types work in the formal setting when you add probability. We've now fixed it, and so now we're going to go back and see whether all of that hard work has paid off for things that we actually care about, which was, first of all, can we actually solve our little problem that we had at the beginning, and have we learned anything else? So the thing that we've actually learned is that probabilistic invariance can sometimes be captured by these simulation relations, and these simulation relations are the things that can be automated, can be checked automatically, and they now, of course, work with probability for us doing all of this sort of hard work. The thing that we understood is that refinement now depends on information leaking through hidden information, which we're now forced to have. So here's a little cadenza building on what we've done. So unfortunately, I could give a whole talk on this whole thing, but I'll just give you some of the highlights here today. So back to our challenge. So on the right-hand side, this was our challenge. So this is not a data type, obviously, but now we can think of it sort of in a data type simulation sort of way. And on the left-hand side, we have a program which is much simpler, and it obviously does the right thing. Why does it? It obviously sets C to a uniform distribution. Why is that? Well, because it only has a single variable. It only has, inside of the loop, it only works on 2 variables, V and T. And it has these 2 guarded commands, and it's got a bit of probabilistic information here. It's got an N over V, which is quite wacky. And then it's got this other thing. But essentially, it doesn't do anything to C. It just does this stuff. And finally, it terminates. And then we set C uniformly to 0 and N. So that obviously sets C uniformly to 0 and n, but that's not something, that's not giving us the allowing us to have the program with all the constraints where we can only have a 1/2 probabilistic choice, okay, which is sometimes a constraint that you have in randomized algorithms. So, however, we can use this idea of simulation because we can come up with a simulation relation which works, which essentially gives us a probabilistic context of C. So it's something like, it's a little bit more complicated than that, but it's something like C is set to a uniform distribution depending on the values of V and T. And so when we do that, we have this very short thing that we have to do, proving simulation relations between the yellow and the blue and the green. And what that does with, we've got to have some extra theorems about, looping behavior, so infinite behavior like that. But what we get is a almost sure simulation between the thing on the left and the thing on the right. And the properties that this satisfies is, first of all, that this terminates, and then it sets something easily to a uniform distribution. So this obviously, with a very quick proof using PGCL properties, this easily satisfies. Then we have this extra thing of having to set up a simulation, but we're no longer having to have some complicated invariant thing involving all of the probabilistic behavior. All we have to do is we say the only behavior that we care about is that certain settings of C are uniform throughout this behavior, and we can capture that very simply using the simulation. And this can be automated. So we're currently working with a group in Aachen under Professor Joost-Pieter Katoen's group in Aachen, who are developing a deductive verifier which works with all of these kinds of things. So very shortly, we're going to have an actual automated proof of this program, but there will certainly still be challenges after that. So the second thing I just wanted to touch on very briefly is that what we learned through going through all of that was that there's this problem of information leaks. So for him, he needed to ensure that information didn't leak early, because otherwise the properties that she was hoping to rely on would not hold anymore. But that's sort of like preventing information leaks. So what this now means is that because we've had to understand all of that, suddenly we can actually start asking questions specifically about other kinds of information leaks. So there are lots of systems, for example, where there are sort of these side channel leaks in various types of programs and so on. And the verification is either showing that there are no information leaks or that the information leaks are very, very small. And now that we've gone to all the bother of trying to understand how to get refinement, how to understand sort of top level properties and to make sure that the things that implementing that don't spoil those top level properties are all to do with inadvertent leaks. And so now we have a system as well, which we're also applying to be able to prove that various sort of security systems don't leak too much information, or maybe don't leak any information if they're done properly. So conclusions for today is, well, we started with trying to find good proofs that can be automated, and we ended up having to go and look at a different problem to do with, which can be described as abstract thinking and abstract data types. We tried to put probability in, we found it didn't work, we figured out why it didn't work. And then once we had all of that understanding, we are now able to push automated verification via simulation relations and proofs, short proofs of simulation relations. And we can also talk about information leaks. And so that's all I wanted to talk about today. So thank you very much.
All right. Thank you very much, Annabelle, for the thought-provoking talk. And I'm going to applaud on behalf of the audience. And it's really nice to see that the programmer in your story actually had the right instincts. It just needed the proper mathematics to account for those instincts. Okay, so we're happy to take questions. So if you can please put the questions in the Q&A or raise your hand if you prefer to ask the question verbally. And we'll be happy to unmute you and you can ask the question. So we are going to be watching. Okay, we have a question in the Q&A from Siddhartha. How can we find out the time complexity of any probabilistic program?
Yeah, okay. So so there's different ways to think about time complexity. One would be just to do a traditional sort of analysis, the sort of things that algorithms experts do. And normally they use sort of like just sort of normal mathematics to analyze an abstract program. But the system that I and colleagues developed, and that's continuing to be developed by other people, sort of Benjamin Kaminsky and Joost-Pieter Katoen and a whole bunch of other people, what you can do is that you can actually use the PGCL system to describe, so if you want to describe performance properties of the program, and then you can use the quantitative semantics to come up with average case analyses of programs, which can sometimes be quite interesting. And these things can also be checked sort of automatically as well, provided that you do those things. So it depends exactly what you want. If you want to like the traditional sort of complexity analysis that algorithms experts do, then those are the sorts of methods that you use there. But you can actually use some of these automated systems to be able to get some more detailed information about a particular implementation.
All right. There's a follow-up question, I guess a foundation question. Can we write abstract program for halting problem? This may need a bit more context. Or
well, I don't know. I mean, I've seen, well, I mean, like with my students, you do something which is try to get the idea of the halting problem. But I've never actually tried to formalize that kind of thing because it's a bit odd. But people do try to use, you know, like more high level notions of writing programs in order to give the flavor of the halting problem. But that's not what I've done.
Okay. Since there's no more question yet, I take the opportunity to ask a question myself. So it is very interesting that I mean, standardly you have traditionally you have the functional verification and you have the security verification, information flow verification, which have quite different flavors. And now when you bring in probabilities, you open the door for information flow tracking, which, as far as I understand, is standard, not probabilistic. It's sort of the usual tracking of flows from the hidden state, right? So is it completely separated? Can you use off-the-shelf tools for tracking non-interference, for example, to support your verification efforts for programs?
So for probabilistic programs or for standard information flow? Sorry, I didn't quite get the question.
No, I'm saying so. Okay, so your goal, let's say we set up the goal of verifying probabilistic programs, functional properties for probabilistic programs. and or data types, but then you're using information flow tracking as an auxiliary, as far as I understood, right?
Yes, yes, in this.
And can you use off-the-shelf tools for checking non-interference to support your verification?
To be honest with you, I don't know. I know that, well, depends what you mean by off the shelf. I know that there are people working with Isabelle who look at, like, let's call it standard information flow, but I'm not sure how much off the shelf they can verify information flows with a lot of hard work. Is that off the shelf?
Yeah. I guess imagining that you are targeting let's say a Java-like program with probabilistic choice with some probabilistic library, and you have this let's say security type systems for tracking non-interference. So would they do, or you need something more custom for your purpose?
So as far as I know, the only sort of proving systems which have probability in are either things like Isabelle, where you have to build the whole theory up for probability, and then also in programs. So what, and to be honest, I don't know how far that's progressed. What I am a little bit more interested in is the work that's being done at Aachen, where they're using essentially something which is a probabilistic, well, they're developing something which will become a probabilistic version of Daphne, right? So that you can essentially have these pre and post conditions, and then it's got all of these sort of automated sort of checking, but we're hammering it with all of these. I mean, it's like a 5-line program and it's still hard, but that's what we're pushing. So as far as I know, there's no very well developed system which works generally for everything. No, it's not like now you have Daphne, so write your program and start using the Daphne tools, or use Isabelle and all of the wonderful libraries and so on that people have developed for. I mean, I don't know whether Java's got the semantics or whatever. I know there's a C semantics or something which works then, I guess, with Isabelle.
Yeah. They have the sort of formal semantics developed for a fairly large subset of Java. But yeah, definitely when you factor in the probabilistic component, definitely.
I mean, so people are working at it around the edges, but I wouldn't say that it's like mainstream yet. Right. I mean, it's hard. So
yeah, exactly. We're very much looking forward to the Aachen tool. So we have a few comments. Very nice talk. The corresponding paper of this talk inspired me to read the book, The Science of Quantitative Information Flow. Thanks. This was a comment from Kang Feng Ye. And then we have apart from other compliments, now we have a question. Can you provide me? Oh no. Sorry. Yes, attendance letter. So yeah, we can discuss some other time. Somebody wants an attendance letter. Okay. Happy to provide one. It's not a problem. Okay. Let's see. John Tucker asks, does PGCL have much of a theory, a classification of its computational power, logics that are complete, etc.? What relation does EADT have with ADTs?
So what's EADT? I don't know what that is.
PADT, I guess, probabilistic abstract data types.
Oh, with abstract data type. Well, so I don't know. Oh, well, so there is a lot of theory in various forms for PGCL. We don't have completeness, which is very. It's not that it doesn't exist or anything like that. I just haven't had time to think about it, but it is a very interesting idea. It's a very interesting thing. I would really like to figure it out. I know that in standard abstract data types, there are completeness results. various kinds. There's a really nice one that maybe I'm a bit biased or something, that came out, I don't know, 20, 30 years ago or something, which was a single complete rule for data refinement, data types. We do not have that for probability. That is definitely on my list to see whether simulation, and there's a simulation relations, which I showed you today, but there's also the co-simulation where, you know, the rep goes the other way around. And possibly those two together would be complete, but we have not yet done that. But there's a lot of theory on the POMDP semantics and the Markov decision process semantics, not just by me, by lots of people as well, and lots of different types of logics. There's a whole massive literature on model checking and temporal logic, probabilistic temporal logic, concurrency. There's a huge amount on that. So there is a lot of theory, but I think it would be really great to get some of this theory really working in practice.
Okay, and as usual, please, if you feel like you should follow up, please feel free to raise your hand, and you can have a more interactive version of your question, John, if this is the case. In the meantime, may I ask another question? I think one of the areas where they are really interested in having practical tools for program verification, and they were able to achieve quite a lot of progress, is in verification of cryptographic algorithms and cryptographic protocols.
Yes.
And you mentioned side channels and an interest in using your methods to address this, or it was not clear to me whether the information flow side or the probabilistic side as well. So will you have things to tell to cryptographers as well with your work?
Yeah, so that's very interesting. So you're right. Sorry, I didn't mention this. There's a lot of work on proving cryptographic algorithms do what they do. So I wouldn't know, whether I would be able to contribute there, but we have had a look at some related topics, obviously sort of in privacy, which is one aspect, but there's also some kinds of so I've worked with some people on with some colleagues on using cryptography, which has been designed so that certain things are leaked, but you don't want too much to be leaked. And the problem there is that there is a relation that once you start having the cryptography, and suppose you've proved that you've got some order preserving, property preserving cryptography. Okay, so that's what we've been sort of thinking a little bit about. So now you've got some perfectly working cryptography which preserves some property of the original plain texts, right? So then you start programming with that thing, but the problem is that sometimes more information leaks out once you start using it, right? And the little bits of information accrue and accrue and accrue until it becomes a big. I don't know the difference between big and small. So at some point it's a problem.
You'll put a number on it.
Yeah. At some point it's a problem. So not necessarily the number is important, but the fact that maybe you can see the rate at which
the growth,
the growth, something like that. And so those kinds of techniques might be interesting for people programming with these specialist kinds of cryptography.
Right.
Because it can be very surprising about what information is leaked. And even if it doesn't matter, it's probably better that you know than you don't know.
Yeah, so you have sort of control on the amount of declassification. So
right, exactly. So there's those kinds of applications. So maybe not with actual cryptography, but maybe with uses of certain types of cryptography.
Right.
Anything that leaks little bits of information, and over time you kind of want to know, is it a problem yet? So.
Okay, interesting. We have another question by Tim. He would like to ask the question. Let me allow him to talk. Tim, please, you all have the floor.
Okay, thank you. Can you hear me all right?
Yes,
Yes,
we can.
thank you. Yeah.
Yes, in your your examples with the user side and the implementation side. On the implementation side, you used an imperative programming style or sequential programming style. I wondered, have you considered using a functional programming style instead? Would it make any significant difference to your general thesis?
Yeah, so thank you for that question. I have, you're right that we were using imperative. I have not thought about how this would work out in a functional programming setting. I know people have thought about these things in a functional programming setting. So I'm terribly sorry. I can't say whether it would make a difference, but usually when you add probability, it does make a difference. But that's just my feeling. So sorry, I can't give you a definite answer, but certainly for sure, other people have worked with probability, I think, and functional programming, but I have not.
Okay, thank you.
I guess, yeah, the monadic approach would, scales well.
Yeah.
The fact that you have already formulated the mathematics in terms of commutative laws in monads and so on, it helps with addressing the functional world as well.
Yeah, well, it's essentially we do have a an implementation which can interpret, probably not using the right words, but it's all in it's all sort of using the monadic structure. You could Tom Shriver's put together a tool which essentially allows us to understand these sort of like complicated hyperdistributions using sort of a monadic approach and clever functional stuff. But I don't know how it works, but it is good.
Yeah, as a general comment, so it would be really interesting if this great theory makes it into verification tools, because we need sort of this more complete methods, this ability to tackle arbitrarily complex programs.
Absolutely, yeah.
Okay, so there's another question from Siddhartha, which I guess is a bit general. For equivalence checking, abstract code is good. So I guess it's a question about the level of abstraction versus the notion of checking equivalence, the relationship between equivalence, program equivalence, and refinement in the context of probabilistic programs.
Yeah. Yeah, I'm not sure the comment. I mean, usually sometimes you want a complex property, but oftentimes you want a simple one, like in our challenge program. But complicated stuff happens, and far too much complicated stuff happens. But you need it. You know, if you go back in time to school, when you were looking at these probabilistic generating functions, you know, quite quickly they became rather unpleasant. And we were just shown the nice ones that could go in textbooks.
Yeah, and there is a resurgence of let's say probabilistic methods taught in the undergrad curriculum now, in using Python and AI based tools and so on. So sort of there's a renaissance of probabilistic programming and a renewed interest.
Oh, good. Yeah.
Okay. So if there are no more questions or people raising hand, I suggest we stop here and thank Annabelle very much again for this wonderful talk.
Thank you.
And many thanks to all of you for attending. And all the best.